So hi everyone, I'd like to once again welcome each one of you to the Pi seminar series dedicated towards advancements in scientific machine learning. Today we have with us Dr. Amirhossein Arzani, who is a tenured associate professor at University of Utah, affiliated to Scientific Computing and Imaging Institute, and also the Mechanical Engineering Department. He obtained his bachelor's, master's, and PhD degrees in mechanical engineering from Isfahan University of Technology, Illinois Institute of Technology, and UC Berkeley, respectively. He is the director of Computational Biomechanics Group at Utah and a recipient of the NSF Carrier and NIH Trailblazer Awards. His research interests include scientific machine learning, fluid dynamics, and biomechanics. So today, Professor Arzani will be going to talk to us about the topic on the title, XAI, which is Explainable AI for Science, from Dynamical System Discovery to Interpretable Operator Learning. So over to you, Professor Arzani, for the rest of the session. Thank you.
Thank you so much. It's great to be here, and thank you for the introduction. So, as we all know, deep learning has become pretty popular in physics-based systems, whether that's topics such as super resolution, denoising, predicting flows, or just surrogate modeling for in-loop calculations like uncertainty quantification or optimization. But however, there are two key challenges in scientific deep learning. The first one is interpretability, and the second one is generalization, particularly to out-of-distribution data, or really extrapolation. So interpretability is important because, well, first of all, we're usually interested in physics-based systems. And also, getting understanding of the system is important, which is not easy with black box models. And also, interpretability can provide a trust in our predictions. And finally, it's helpful for debugging our models, because if we know how our machine learning model is making its prediction, that can help us better debug our models. And then also extrapolation, or out-of-distribution generalization, to some level is important. Of course, we can never hope to extrapolate far unless we're really lucky. But to some level, that's important once we deploy these models in practice, because in many applications, we don't exactly know the boundary of the training landscape, or that might be a little bit blurred. So having models that are a little bit robust to extrapolation, at least to some mild level, that's really useful for practical applications. So in this talk, I'm going to be mainly focusing on the interpretability aspect, but I'm also going to touch a little bit about generalization. Okay, so this brings us to the field of interpretable and explainable AI, or XAI. So we can broadly divide XAI into two topics. We have the by-design approaches, where we incorporate interpretability from the very beginning into the architecture of our machine learning model. So just by construct, our model is interpretable. The issue here could be limiting expressive power, because it's more difficult to fit very complex data with this approach. And then we have post-hoc approaches, where we interpret opaque deep learning models as a post-processing step. So here we do not compromise accuracy, and we're just doing interpretation as a post-processing. So for by-design approaches, we have methods like SINDy or symbolic regression, and for post-hoc approaches, there are some tools like SHAP or gradient-based approaches for interpretation. Okay, so this is an outline.
Amir, just one question.
Yes.
Can you explain more about post-hoc approaches?
Yeah, sure. So I'm going to talk a little bit about it in the talk today too. But essentially, what you do in post-hoc approaches, you basically take the neural network. Let's say you take an input that you want to explain, and you want to see how that input gets mapped to the output. And then what you do is that you fit a simple linear model, maybe. Like, there are many approaches to do, but one way you can do it is that you fit a simple linear model locally around that input. So basically, using the neural networks, by probing the neural network, you can fit a simple model to the neural network's prediction locally and use that simple linear model to make predictions. So that's one approach to do it, but then you can also use other approaches as well. So I'll talk a little bit more about that in the second part of the talk.
Okay, thank you.
Okay, so the first part of the talk, I'm going to be focusing on dynamical system identification, discovering analytical differential equations from data. And then the second part of the talk, I'll talk about interpretable operator learning in the form of integral equations. So dynamical system identification. So here's the problem. We assume we have some data. This is trajectories for some system. And our goal is to find the dynamics of the system in the form of analytical equations. This could be either ODEs or PDEs. So there are different ways to do it. We can use symbolic regression. We can use the sparse identification of nonlinear dynamics method, SINDy. And also we can use an opaque approach using deep learning. The first two approaches are interpretable, and deep learning is, of course, not interpretable. And the focus of today's talk is going to be the interpretable approaches. So in symbolic regression, what we do is that we have some data and we fit an analytical equation to the data. This is done using an unstructured search algorithm. We basically search for different mathematical operations like addition, subtract, divide, and then we do some nonlinearity like exponential signs, and we look into all possible combinations of these operations to come up with an analytical equation that fits our data. And this is typically done these days with genetic algorithms. It can optimize, find a complete set of equations with nonlinear parameters, but sometimes it leads to these so-called bloating effects, which leads to a dense model with many terms. And it's also computationally expensive. And every time you run it, sometimes it can lead to different answers as well. On the other hand, we have the SINDy method, which is based on a structured search algorithm using convex optimization. It's pretty much just sparse regression or lasso method. It needs a candidate matrix for candidate terms. And also the main issue in SINDy that we want to talk about today is that when we use SINDy, we need to exactly know the system parameters like Fourier frequencies, exponential growth decay rates, polynomial orders. All these things, we need to exactly know them beforehand. So that's a severe limitation. But the benefit is that usually we can control how interpretable model we get, and also it's computationally efficient because it's an efficient, convex optimization problem. So now, if you put these two methods together, our goal here is to come up with a new approach that's somewhere in between the two methods, and this is the new ADAM-SINDy method. It's based on a structured search algorithm, just like SINDy. We use a fully adaptive lasso method where we can apply adaptive candidate-wise penalty, and I'll talk about this more later. And the main advantage here is that we can optimize all the system parameters. So unlike SINDy, we don't need to know beforehand what are the Fourier frequencies or exponential bandwidths. We can find them, define them as unknown, and optimize for them. And it has some other advantages like self-interactive terms that I'll talk about, and it gives us an interpretable model. And compared to SINDy, it's more computationally demanding, but the cost, I would say, is less than symbolic regression. So the computational cost sits somewhere in between. And finally, in a very certain class of problems, we can also incorporate physics-based laws into the optimization framework, which I'll show. Okay, so let's focus on SINDy and ADAM-SINDy. So this is the classical SINDy approach. We consider dynamical system, x dot equals f of x. And the problem is this: we assume we have trajectories. We have x as a function of time. So we have the solution, basically. And what we want to find is that we want to find an analytical equation, f of x, that represents our data. So the way we do is that we take our trajectory that we have, we calculate the derivative, temporal derivative, for example, we find a difference, and then we construct this library of candidate terms. We basically throw in anything we can think about that can possibly appear in f of x. Polynomial, sine, cosine, exponential, all their interactions. So we create this huge library of possible candidate terms. And the problem here is this: once you deal with sine, cosine, tan hyperbolic, or exponentials, or even like powers, these parameters are now nonlinear. So these ABC parameters, you need to know them exactly beforehand, or you need to guess them. Otherwise, as I'll show later, SINDy will not work. And then you formulate this sparse regression problem, very standard lasso regression problem where you use L1 norm to promote sparsity, and you can solve this regression problem using a standard convex optimization algorithms. Typically in SINDy, the gamma matrix is set to identity. So we just uniformly impose sparsity. Okay, now in ADAM-SINDy, we have the exact same problem set up. It's exactly the same. The only difference is now that we also make the nonlinear parameters so these are these lambdas, we make them also trainable. So we're not assuming that we know them, but we can also solve for them. And also, so these nonlinear parameters are now trainable. And also what we do here is that we basically can also adapt for the sparsity promoting parameters. So typically either lambda, which is a uniform sparsity knob, or gamma, which is like a candidate-wise sparsity. Either we can select one of them and make either lambda or gamma trainable. And that has benefits because we show in our paper that can reduce sensitivity to initialization of these parameters. So you don't need to do an extensive tuning like you need to do in SINDy because it's trainable. And also, as I'll talk about later, when we make gamma trainable, like candidate-wise sparsity, we can reach machine precision accuracy. But if you just focus on lambda, don't do it candidate-wise, we still can get good results, but it's more difficult to get machine precision accuracy. Now, this is a min-max formulation problem. This is exactly like self-adaptive pins. So if you're familiar with in physics-informed neural networks, sometimes we have different losses like data loss, equation loss, and sometimes we make those weights also adaptive and trainable. And this is the self-adaptive pin method, and that also uses a min-max framework. So we use the same setting here, but the interesting thing is that originally in our first version we didn't do min max, we did min. So they're both mean, and theoretically when you do min, you expect gamma to go to 0, but what we saw is that if you initialize it with large parameters, it actually still converges and gives exactly the same results as the min max approach. The only difference is that in the min-max approach, which is compared to min-min approach, it's more robust. It's more robust with respect to how we initialize these sparsity parameters. So there's like a wider range of initialization that the method can still work. Okay. Now, ADAM-SINDy is also, there's more connections with PIN. And in fact, the method was completely motivated by PINs and specifically adaptive activation functions. So in physics-informed neural networks, as you know, we represent functions as variables as functions of space and time, and then we basically simultaneously optimize everything, all the weights and everything. And a new method that actually was proposed by Ameya in a series of nice papers is this adaptive activation functions, where for the activation functions in these neural networks, typically we use something like tan hyperbolic or swish, where they have a fixed slope. So for example, with tan hyperbolic, typically we have a set to 1. So we have this activation function. But if you make the tan hyperbolic activation function adaptive, you introduce this coefficient a, so have basically a tan hyperbolic of ax instead of just tan hyperbolic of x. And this could be for other activation functions too. And you make this factor a, this single coefficient a, also trainable, then you can adaptively change the slope of your activation function, and that gives you tremendous flexibility in fitting, solving complex problems. So what we're doing is ADAM-SINDy was entirely motivated by this approach, which was promoted and came out from Ameya, and it's basically exactly the same because these adaptive activation functions have nonlinear parameters, and it's the same in SINDy. We have these sines, cosines, exponential terms that have nonlinear parameters. So we said, okay, why not we make them also trainable? And we can afford to do that because we're no longer treating the problem as a convex optimization. We're doing ADAM optimization, just like what you typically use in PIN. So because we're doing a global stochastic gradient optimization, we can afford to introduce this nonlinearity into our optimization problem. So that's the key, contribution of ADAM-SINDy. Okay, so now here's the problem statement. We're going to have this master library. We're going to have this huge library of all these candidate terms. We're going to look into two different SINDy methods. The SINDy width method is going to assume that I exactly know the nonlinear parameters. And this never happens in practice, but this is just to show you that if you happen to exactly know the nonlinear parameters, SINDy works perfectly. There's nothing wrong with SINDy there. But if the SINDy without method, which is the more realistic method in practice, assumes that we don't know the nonlinear parameters, and what it does is that it guesses them, and we assume the ground truth is somewhere interpolates the values we guessed. And then, of course, in ADAM-SINDy, these nonlinear parameters are trainable. In SINDy methods, we tune the lambda parameter, the sparsity parameter, but in ADAM-SINDy, that's adaptive. And we solve them with convex optimization, with ADAM method, global optimization, ADAM-SINDy. And finally, these are the two different optimization formulations. In ADAM-SINDy, we also have the option of doing batching, or we can do full batch. Okay, so here's the first example, Fourier, a harmonic oscillator. And what makes this problem, this is the ground truth system. What makes it difficult is that you have this frequency inside the cosine term, which is not trivial. You might not know what that is. So in SINDy, if you exactly include that, you happen to know the frequency, which is typically not the case, and you include it in your library, you get the exact correct solution. But if you don't know it, this is what you get. You get this very dense model, which interestingly, in this case, it can still fit the data. So you're getting like a dense model that fits the data. No, it's accurate, but it's not the same equation and it's not interpretable. So probably doesn't generalize as like the ground truth model. And then, but in ADAM-SINDy, this frequency is also trainable. So we can also exactly find that frequency. Okay, so the next example is van der Pol oscillator. So here we have this 2.15, this polynomial degree, which is not trivial. Again, in SINDy, if you exactly know it, you can solve it. If you don't know it, you'll get something that's not exactly the same equation. But in ADAM-SINDy, we can still make that trainable and solve the exact equation. Now, here's an interesting thing that happens in ADAM-SINDy. You can see that in this example, it's trying to pick up an exponential term by mistake. It picks it up by mistake, but what happens is that because the exponential bandwidth is also trainable, it converges to 0, and that exponential term becomes just a 1 term, and then you get these 2 y terms in the final answer that you need to actually manually add them. So the algorithm doesn't add them for you. You just need to look at it, inspect the final solution, and manually add them together to get the final correct answer. Now, this is not a problem here, this self-interaction of the terms, because we're doing global optimization. It's a stochastic gradient descent optimization, so it doesn't cause problems for convergence of the algorithm. Okay, now the next example is doing something like physics-informed SINDy. So this is for the ABC flow example. So I'm going to compare it to PIN. So in PIN, of course, you can have adaptive activation functions. You represent your variable like velocity, for example, using fully connected neural network as a function of space and time. And you have data loss and you have equation loss. And of course, you form this computational graph. You can use automatic differentiation to build your governing equations. Now, in ADAM-SINDy, we also have this nonlinear candidate function class, where it's kind of similar to adaptive activation functions. And if we are solving if the state variables are velocity, what we can do in SINDy is that we can impose the physics using an equation loss. And this is how it works. Now, what we do is that in the sparsity part of the optimization, instead of an adaptive candidate-wise sparsity parameter, we change that to the divergence of the equation. And here, the left-hand side, here we're solving for a flow. So the left-hand side is velocity. So x dot now is velocity. So we can take its divergence using automatic differentiation, and we can weight the sparsity term with the divergence. So I'm going to show you what's the benefit of that. So here we're kind of like imposing 0 divergence as well, or reducing divergence. So that's this kind of like a physics-based loss here incorporated in SINDy. But I should tell you that this only works for a very, very specific class of problems. That's the difference between PIN and this new physics-informed SINDy here. With PIN, you can impose any physics, any differential equation, right? But here, you need your dynamical system to be in a very, very specific type of problem so you can add this physics loss. So for example, in our case, the ABC flow example that I'll show you in a second, the dynamical system is basically just velocity field. You have trajectories, tracers, and you want to fit an analytical velocity field into your tracers. So this is the kind of problem, if you know the flow is incompressible, you can add the divergence-free condition as a equation loss. The other examples would be maybe Lagrangian, Hamiltonian dynamical system. So there's a very specific type of problems where we can use physics-informed SINDy. Okay, but the ABC flow is one example. So here, this is the ground truth. So ABC flow is a basically a benchmark problem in a chaotic advection. It's a chaotic flow. It's a 3D chaotic flow problem, a benchmark problem, and it's divergence free. And here we modify the ABC flow to make it even more complicated. We're introducing multiple different frequencies here to make it very difficult for SINDy to find the equation. And we have two approaches. We have the approach without physics and the approach with physics, where we add in divergence free condition here. So here's the ground truth. So in SINDy, again, if you happen to know all these frequencies, no problem, you can solve the system. But if you don't, you get this dense model. Now in this problem, because now we're going to a chaotic system that's more complicated, this dense SINDy model cannot even fit the trajectory. So in the previous cases, it could at least fit the trajectory, but here it can't even fit the trajectory. Now, in ADAM-SINDy, what we get is that we can solve exactly, and we can find all the frequencies without any prior knowledge about them. Now, the thing is that you notice that I put pi here for all these frequencies, and what that means is that all these frequencies that we find were accurate up to machine precision. So we were able to get, and this is the case for all the examples I'm showing today, is that all the results we get are all accurate up to machine precision, and this happens with this adaptive candidate-wise term gamma. So if we take away this gamma and you only have lambda, what we saw is that we can still solve the problem with ADAM-SINDy, but we get a little bit error in our frequencies or in our terms. But once we introduce this adaptive candidate-wise sparsity term, gamma, then everything becomes machine precision accuracy. Okay, now here's the benefit of physics constraints. So in this problem, I can have the divergence free condition. Now, if I include that or I don't include the physics informed loss, both approaches, I get the exact same answer. So both approaches give me this. But the difference is this, as you see in this plot, is that in the physics informed case, the optimization problem converges in less than 40 epochs, whereas without the physics, you need 60,000 epochs for the ADAM-SINDy to converge. So it makes the algorithm much faster in this case, which is pretty interesting. And this is actually very interesting because it's opposite to what you see in PIN. In PIN, whenever you add the physics-informed loss, you basically make the optimization more difficult to converge. But again, I should reiterate that physics-informed SINDy is not for any differential equation. Very, very specific class of problems. Okay, the next example is chemical reaction kinetics. So here we have an exponential term that we don't know this exponential parameter. So SINDy can work if you know the exponential parameter, but if you don't know it, you get this dense system that's even slightly deviates from the ground truth. But in ADAM-SINDy, we can precisely find the equation with the exponential parameter. Now, this specific example was taken from a recent symbolic regression study using neural networks. So we can compare results with their symbolic regression approach. So we see that without, in their first attempt, without what they call explicit stacking, which is explained in the paper, but the equation that they got for this problem was a dense model. So this is what symbolic regression gave you. So they had to do specific treatments in their method to be able to get the correct solution. But you can see even then, they now do get the correct terms. But if you look at the parameters, there is some error in most of their parameters compared to ground truth equation, whereas in our method, we have exactly the same answer. Okay, now, again, because we can get machine precision. So the next example is pharmacokinetics. So this is an example of a time-dependent reaction. This is what we call non-autonomous dynamical system. And again, we see the same results that, SINDy, without knowing this power term, the power in time, cannot get the right equation, but in ADAM-SINDy, we can optimize. Okay, the last example I have in this part is a PD example. So we can also do partial differential equations. So here we look into a reactive flow example. This is a simple wildfire transport model. It's a nonlinear advection diffusion reaction equation, which you can find more details about the model here. What we see here is that, again, we can, with SINDy, find exactly the terms for this PDE nonlinear reaction model, whereas in SINDy, the classical SINDy approach, which is this here, it's called PDE find. The PDE extension of SINDy, it cannot find those parameters correctly. But in ADAM-SINDy, we can exactly find. Okay, so now I go to the second part of my talk, which is about interpretable operator learning or discovering analytical integral equations from data. So for this part of the talk, I want to start with this functional data analysis approach. So in functional data analysis, which is a branch of statistics, we analyze data in the form of functions rather than discrete data. So this is what operator learning basically is. But I want to mention that, right now there's a lot of interest in operator learning in different groups, but operator learning really dates back to this field of functional data analysis, which is a lot of progress was made in FDA by the statistics community in the 90s. And there the goal is pretty similar to operator learning. The goal is that you have some input function f of x. You want to treat it as a function rather than a discrete data. So you want to account for x, basically. And you have an output, which is either u of x, or it could be a single scalar value u. And your goal is to find a mapping that takes you from f of x to u of x. Or if your output is a single scalar from f of x to u, so for example, maybe f of x is a velocity field and you want to map velocity field to pressure field. That's one example. Or in the second case, maybe your input field is a velocity field or vorticity field, and you want to map it maybe to the lift coefficient or drag coefficient, or maybe maximal wall shear stress. So like a single value. The simplest way that you can think about doing this problem is a classical regression approach, where you formulate this simple classical regression where the goal is to find this bias coefficient function A and this bias regression and this regression coefficient function psi. But the problem with this approach is that the regression problem is formulated completely local. Okay, so it doesn't look into the neighborhood effects of points X. So it's really limited in terms of utility. The more appropriate approach is to use these kernel approaches, the simplest one being this functional linear model, where now you use these integral equations. You have this dummy variable zeta where you integrate over, and you can evaluate the solution at any x that you want. So now the goal is to find this kernel style, okay? And you can do it from function to function mapping or function to scalar mapping. So now in this approach, you're going to be using neighborhood information from the input function f to make your prediction. So it's going to be much more accurate. You can control the level of non-local information that you're incorporating into the model using the bandwidth that usually you define in your kernels. So our goal in this part of the talk is to build on this very simple functional linear model for a kind of an interpretable approach towards operator learning. So now the problem here is that how do we find this kernel? In the classical approaches, this is how people did this, in the 90s with the FDA approaches. They typically predefine a basis for this psi of x, these kernels, and then they kind of like solve the problem with predefined basis. In modern approaches, what we do is that we use neural networks to find this this mapping. So either different types of neural operators like FNO, DeepNets. So we use this type of tools to do this mapping. Now, what we want to do in this talk, we want to do something in between the two approaches, in between the classical approaches and the modern approaches. Okay. Now, before I explain how we do this, I want to motivate this a little bit more under this umbrella of theory-guided machine learning. So what I think about theory-guided machine learning is that doing machine learning, but using theory, classical theory, to guide how you go about doing your machine learning problem. For example, in physics, when we deal with PDEs or physical systems, we see that integral equations happen a lot. Like in linear PDEs, you always have these Green's functions that you can use to find the solution, right? And that involves integral equations, you have convolutions. So integral equations happen in many different physical systems that map functions. For example, when you want to map vorticity to velocity, there's like some theorem in fluid dynamics that you have some integral equation approaches. So these are pretty interesting. So now the goal is that can we build a machine learning model somehow being inspired by that? So somehow building on integral equations, because we know they're like everywhere in many different physical systems. So this is what I mean by theory-guided machine learning. And you can contrast that with the physics-informed machine learning, for example, PIN strategy, where in PIN, the physics is typically a regularizer through a loss function. But when we think about theory-guided machine learning, the way I see it is that in that approach, physics or theory guides how you design the architecture or what type of model you use for your problem. Now, one example of that is this boundary layer pin approach, which is kind of like actually both of these two approaches. So here, if you're interested in solving singularly perturbed differential equations, so basically boundary layer transport problems with very thin boundary layers, that pin fails. And what we did here was that we incorporated the classical perturbation method and asymptotic expansion approach and use that to guide the design of our pin architecture. So we set these ensemble pin neural networks to replicate exactly what happens in the classical perturbation and asymptotic expansion theory. So this is an example where the architecture of the pin method is guided by classical mathematical theories. Okay, so we kind of have the same motivation here too. And this brings us to this interpretable operator learning problem. And our goal is to build a surrogate model as a linear sum of integral equations. So something that looks like this, which you can write down in a closed form solution that can map any input function f to an output function u. And the goal here is really to learn these kernels or learn these integral equations. And you can make these input functions f, you can include nonlinear transformations of that, like f squared as well, to augment these terms. Now, you can do this in both post hoc approach or by design approach, if you remember the beginning of the talk. So in the by design approach, what you do is that you forget about a neural network. You don't even consider any neural network, okay? You directly take your input-output functions, your data, and you directly fit this integral equation model into the data. So this is a by design XAI approach. In the post hoc approach, what you do is this. You train a neural network. So this could be any neural network or an operator, a neural operator that maps the input function to the output function. And then what you do is this. You probe the neural network in any desired landscape that you want. You give it a bunch of input f's, and the neural network will quickly give you an output u. And you can do this locally, globally. You can do this for out of distribution. You can do whatever you want, however the region you're interested in fitting this surrogate model. So this is how you generate your input-output pairs. And from there, it's exactly the same approach. So just like the second approach that you have them, now you have these input-output functions too, and you can fit this XAI approach. So this approach becomes what we call post hoc, or you can think of it as neural network driven, because you're just using a trained neural network. So now the neural network is already trained. So you're not using data anymore. You're giving it arbitrary inputs. So it's completely neural network driven. Whereas in the second approach, you're not even using any neural network. It's completely data driven approach. So now, before I show you talk about how we actually solve this problem, let me talk a little bit about more interpretability here. So you can approach interpretability in this problem from two different perspectives. From the mathematical perspective, what I mean by interpretability is that the operator learning problem that I have has a closed form solution. There's an analytical equation that I can write. Okay, so I can write the closed form solution for my mapping. Now that equation might be wrong, might be long. There might be many terms depending on how complex the problem is, but I can at least still write down a closed form solution. So that's the first aspect. The second aspect is that there's a sparse set of parameters. So I only have these coefficients W that are the parameters of the model, and they usually tend to be on the order of 10, for example. Whereas in a neural network, you have hundreds of thousands of parameters. So like you're now going to have orders of magnitude less parameters. And number three, your model is additive. So with respect to these parameters, the terms are being added together. So this is pure mathematical point of view to interpretability. But then perhaps what engineers care more about is the physical perspective of interpretability. And this is about using this model to understanding spatial relationships between input and output data. So I'm going to talk a little bit about the second perspective today too, based on our very recent work that's still ongoing. Okay, so now how do we find this analytical equation? So we again use a library-based approach, just like SINDy. So what we're going to do is that we're going to build this huge library, essentially a very big matrix, where every column is all my candidate integral equation. So any integral equation that I think that's possibly important. So different kernels, different Gaussian kernels, different bandwidths, different nonlinear extensions of F. I can put all these kernels, all these integral equations as columns of my matrix. And then the rows are just evaluating these integrals for different training data. So once I have that, I can formulate a regression problem and see what's the coefficient weight for each of one of these candidate integrals. And once I find those weights, I simply add all those terms, and I have my final operator learning problem that has a closed form solution. So now to find these weights, I can do two different approaches. I can use sparse regression. So this is exactly like SINDy. So in this approach, many of the weights W's become 0. So only a small subset of them remain. Or I can do L2 regularization. So forget about sparsity and just use L2 regularized regression, which tends to be more robust in some applications. And depending on what I'm looking after, either of them could be useful. So if I want to have a model with as few as terms as possible, I need to use sparse regression. If I want to leverage the integral equation approach to do physics interpretation, which I'm going to talk about, either approach works. So I might as well just use the L2 regularization because it's a little bit more robust. Okay. Now, here are some examples to show you that this model can fit data. And before I get to the interpretation part, so this first example is the porous media flow problem. I have a heterogeneous permeability field as input. And my goal is to map that to the velocity field by solving the Darcy equation. And I define training data by just analytically defining this complex heterogeneous permeability field. I vary A and B to generate different permeabilities, and that's my training data. And then I also look into extrapolation. So I extend A and B beyond the range that I use for training to also see how the method works in out-of-distribution extrapolation. So then I get the neural network prediction. So you train a neural network basically for this. So you have the neural network prediction, and then you have the interpretable model prediction, which could either be neural network driven. So you can see it kind of looks like the ground truth neural network prediction, or you can have the data-driven operator learning approach where you directly train it on data without even a neural network. So I'm going to call this data-driven, and the interpretable model that's trained based on the neural network, I'm going to call it neural network driven. So if you look into the box plots for these plots for the errors, we have the pointwise error, which is aggregated across all data in a pointwise manner. And this is the image-based absolute error. So what you see immediately is that if you look at the test data, so by test here, I mean extrapolation. So this is out of distribution generalization. You see immediately that the interpretable models can reduce the extrapolation error compared to the neural network. So now we have much lower errors. So this is a typical box plot. So the dots here, the red dots are the outliers. So the majority of the data sits here, basically. And the other thing I see is that for the training regime, the neural network is more accurate, but the interpretable models have comparable accuracy. And interestingly, they actually reduce the outliers too. But the neural network, as you might expect, it has more accuracy in the training regime. Now, I do another example. In this example, I want to map low fidelity velocity data to high fidelity wall shear stress. So my input is velocity data away from the wall. This is a 2D constricted channel problem representing a 2D steady simplified block artery. So my input data is velocity that comes from a very coarse mesh. I even increase the viscosity to represent like a dissipative simulation. That goes to input. And the output is trained based on high fidelity CFD simulation with a very fine mesh with even quadratic finite element shape functions. So the goal is to map the low fidelity velocity to high fidelity wall shear stress. And I train it in a certain Reynolds number, and I look into extrapolation to high Reynolds number. So I have the same plots here, and I see the similar conclusions. For the test errors, what I see is that the the interpretable models, in this case, can significantly reduce the extrapolation error. So you can see in the pointwise case, there are some points that the outliers have higher error, but the vast majority of the data have a lower error in the extrapolation regime. And the interesting thing is that in this specific example, even in the training regime, I can slightly improve the training error for the interpretable models. Now, in the paper, we even looking at the validation regime, which is the interpolation regime, where we present like detailed, much more detailed results for like the validation or interpolation cases as well. Okay, so the conclusion here is that this analytical equation approach at least can improve extrapolation compared to a regular neural network. Okay, now how do we use this for physical understanding? So this was extrapolation, but what about physics? So now what we're going to do, and this is very, very recent work, this part of the work is still ongoing and not published. So the way we approach is that this problem now for physical understanding is that we're going to use the linear integral equation setting of this mathematical problem. So what do I mean by that? So I have an input image. It has a domain omega t. I can take that domain. I can divide it into any arbitrary subdomains I want. So in this case, omega 1, omega 2, omega 3, omega 4. But I can do that however I want, as long as the union of them is the total domain. And since my operator learning problem is a sum of integral equations, and in this case, I do a linear sum, what I can do is that I can break down the total integral evaluation into the sum of integrals evaluated on each subdomain. So if I integrate over subdomain omega 1, I'm going to get certain solution. Okay, so remember, the integration is done with respect to the dummy variable. You can evaluate the integral in any x and y you want. So if you evaluate the x and y everywhere, so we get a full image for output, but the integration, since that's done with the dummy variable, I can integrate in any subdomain I want. And then when I do that, the integral equation, the total integral is the sum of the integrals over subdomains, very basic integral equation property. So I can write my final solution as a sum of the contribution coming from different subdomains. So this is kind of like modes. Of course, these are not perpendicular or anything, but this is kind of like, if you think about, you're breaking down your operator learning problem into different contributions or different modes coming from different regions. So here's a closer look of what that means. Once my operator learning problem is trained, so this is a post-processing step. Once I do my XAI training, I come up with this integral equation model, which is typically a sum of integral equations. I can look into this integral equation, and again, I see that the zeta is a dummy variable, and I'm integrating with respect to omega. So I can take my domain omega, I can split it up into different subdomains, right? This is my input f of x, which is integrated over zeta, and I can evaluate x to be the total domain. That's where the output gets written. So I can break down the contribution coming from every input domain, every subdomain separately, and I can look at them separately. So this is the part that I can use this interpretable operator learning approach for actual interpretation purposes. And because now we're looking into the contribution coming from every subdomain. Okay. Now, again, I'm going to show you one test case. So we're currently working on more cases here. So this test case comes from this pretty nice database coming from Town. I suggest everyone to look into this paper. It's a very nice open source database from different benchmark problems that has different open data for benchmarking different unsteady different spatial temporal velocity or fluid flow data. So we specifically take the flow over a pitching airfoil from this open database. And what we're interested in taking the velocity field as input and mapping that to the drag coefficient. So this is an image to scalar mapping problem. So the velocity field gets mapped to the drag coefficient. So this is the output that we want to predict. And the inputs are these different snapshots at every time step. So this is just trained on a single time series data. This is not trained on a large data set or anything. This is just a single spatial temporal simulation that we want to interpret. Okay, so now here's the results. On the left panel, I have the drag coefficient as a function of time, and the ground truth is blue, and the XAI prediction, the integral equation approach, is the dashed red line. So you can see the XAI can have very accurate prediction. Now, the interesting part is the right plot. In the right plot, what I'm doing is that I'm breaking down the contribution of the XAI approach using the integral equation setting into different zones, where these are like the different zones. And if I sum up all the zones, they're going to be on top of the ground truth. So this curve here is the ground truth. The XAI prediction is also on top of ground truth, and the sum of the contributions from different zones is also on top of the ground truth, because the sum of the different zones is exactly equal to the XAI prediction. There's, of course, going to be some numerical integration error there, but pretty much it's on top of that. Now, if you look into the contributions coming from different zones, for example, you see that zone 4, which is this orange or plot, is the only zone that's exactly following the phase of the data. So the minimum and the maximum phase is exactly followed. The amplitude is larger, but then when you add the contributions from the other zones, that kind of like reduces the amplitude and it fits the data exactly. So again, this is very, very recent result. We're still trying to process this result more. We're going to have more test cases. We're even working on image-to-image interpretation. Stay tuned for more results related to this physical interpretation. Okay, so that was my last slide. So to summarize, we've introduced ADAM-SINDy, an enhanced version of SINDy that can simultaneously optimize nonlinear parameters without their prior knowledge, motivated by adaptive activation functions. It provides a more flexible framework for finding interpretable dynamical systems model. It's all written in PyTorch, so you can incorporate differentiable programming within that too, which is another direction we're looking to investigate. And then the adaptive candidate-wise sparsity approach, which is missing in the classical SINDy approach, can give us machine precision together with ADAM optimization. And the interpretable operator learning model could be used to improve neural network generalization, specifically extrapolation. And also our operator learning framework can be used to understand how input data is mapped to the output. This part is still ongoing work, and we hope to have more results soon. So if you're interested to learn more, you can check out these two papers for the two parts of the talk. And I would like to thank my students, and happy to take any questions.
Thank you, Professor Arzani, for an amazing talk on your work. So right now, I'd like to request participants, the floor is open for questions. Please feel free to unmute yourself to ask any at this point.
ADAM-SINDy, please.
Yes.
And on the assumptions of ADAM-SINDy, as I understand, yeah, you optimize for parameters, but you still have the library of candidate function, but only their structures. Am I right?
Right. So that's absolutely right. So it still needs a library of candidate functions. So it doesn't overcome that issue in SINDy. What it does overcome is that when your library of candidate functions has exponential, sine, cosine, tangent hyperbolic, and like polynomials, non-rational polynomials, you don't know these parameters. So your library, you have to consider a range for them. So your library becomes huge, and assuming your range exactly touches on the ground truth. So that part, you eliminate that part. But the exact form of the terms, like including exponential or not including exponential, that part, you still need to include the correct terms, the nonlinear terms there.
Do you think it might be possible in future to optimize, at least to some degree, to include uncertainty to candidate function structure itself?
That's a very good suggestion. We thought about that. So we've been thinking about how can we make this closer to symbolic regression, basically. Because in symbolic regression, like it iteratively combines different nonlinear terms, for example. For example, you have sine and exponential multiplied by each other or things like that. We've been thinking about how we can replicate those things that symbolic regression does in this setting. So this is still something we're thinking about. It's a great suggestion.
Thank you very much. Thank you for your talk. It was very interesting. Thank you.
Thanks.
Professor Arzani, your previous slide on decomposition of the domain.
Yes.
So you had explained about how you went about. I don't think I.
Yes.
Yeah. So I think yes, this is the one that I was. Yeah. So I was just trying to understand the way in which the training, if it is possible for you to do the explanation, because I know that you did mention it's not published right now. So
it's pretty simple. So the training is done that it's exactly like operator learning. You have some f of x, some function inputs, and you have some functions out. So that's the training of and then we do this. The to find this integral equation itself, that part is published actually. So that part we use is from this paper. So we use this spot regression approach to find this analytical integral equation. So that part, if you're interested to learn more about the details of how we find these analytical integral equations, you can check out this paper. But then for the post-processing part, which is the part that's new,
Yes.
the entire idea is that we have the integral equations now, we find them. So the integral equation is now there. We take the integral, is over a domain omega, which is simply split omega into some subdomains, and just the property of an integral equation. The integral over the union of these is the sum of the integrals. So then you can split the contribution from different domains. Now I have to warn you something. This is not casual. This is not, you still need, this is just correlation. This is just explaining how the model is mapping input to the output, right? This is exactly explaining how the integral equation is mapping input domains to the output. But does it exactly correspond to the physics? That you can never be sure with machine learning, because machine learning causality is an issue. If you want to have machine learning finds correlations, but not causality necessarily. So if you're interested in causality, that requires approaches like interventional methods, but things like that. But what it does show you is that it will explain to you how exactly machine learning model maps the input to the output, how it treats different regions. So it kind of like explains how it's coming up with its answer. Now that the way it's working, it might match the physics. It might not match the physics. Maybe it is looking at something different than what we normally look at when you relate, let's say, velocity or vorticity to drag. So maybe it's looking at things differently, like spurious correlations or something like else. But that's still pretty useful to know.
Right. That's understandable. Thank you for that, Professor. But and another question is like, is the inspiration for this or motivation for this particularly from perspective of parallelization of the domain as such? Or I was just wondering, like, we are breaking it down.
So the motivation why we split the domain to different regions is that this is exactly how classical XAI approaches work. So like Lime, SHAP, what they do, if you look into the image processing community XAI work, with the classical off-the-shelf packages, they take an input and they highlight which region is important.
Okay.
So that's why we kind of are following the same approach. We want to see which region is in the input is important for the specific output response. That's exactly how things like Lime or SHAP, these methods work.
Yeah, so like I've noticed that in explainable for classification problems. So for instance, if you're classifying a cat in an image, you would highlight a region around that cat in that image so that
yes, exactly.
It makes it more explainable for the model. Yeah. So, but I was just wondering, like, for a fluid problem, for instance, that is fluctuating or varying with time, wherein the flow structure can abruptly change from one point to the other. So I was just
So here what we're doing is that. So again, we still have more work to do here, but all we can say is that every domain, what does it create? What output does every domain create? And then when you add the contribution of all 4 domains, you get that final answer.
Right.
So all this is doing is that it's taking the final answer, it's splitting it up into 4 parts, that when you linearly add the 4 parts, you get the final answer. And each part comes from each of these domains. That's all that's happening here.
Okay. I think that. Thank you for that. So, but so there is no particular fashion in which you want to do this. You can even break it down to 8 fragments if you want.
Of course, you can break it down to 8. The sizes could be different, even they don't have to be equal. You can do whatever you want, as long as the sum of the unions are the total domain.
Right. So thank you for that, Professor.
Yes.
Amir, I still have 2 questions. So first one is, can you clarify how these NN-based, NN-driven post-hoc models are interpretable? I'm still, it's not clear to me.
How the post-hoc models are interpretable?
Yes.
Okay, so again, there's a 2 perspective. Mathematically, it's interpretable because it has less parameters. That's as simple, and you have closed form analytical solution. That's all there is. You have a limited number of parameters. You can analytically write it down. It's closed form mathematical representation. So that's just from the pure math perspective.
So it depends on the size of the neural network, right? So we cannot go for very deep neural network here.
No, I'm talking about this model.
No, I'm talking about the top one, and then
the post-hoc one. How about the post-hoc approach?
Yes.
Okay. So in the post-hoc approach, you take any neural network you want, any architecture, it doesn't matter. It's like agnostic to the architecture. Any architecture you want, very deep, shallow, CNN, fully connected, FNO, whatever you want, you take it because it's already trained. So remember, this is an already trained neural network. Then you give it any input you want, or a bunch of inputs, basically. Any input you can define, because once it's trained, if you give it any input, it gives you output. That's what a neural network is supposed to do, right? So you probe it with any desired set of inputs that you define arbitrarily yourself, and you get quickly, you can do that because it's inference, right? You quickly get that. Once you have these pairs of inputs and outputs, now you fit this surrogate integral equation to these pairs of inputs and outputs.
Okay.
So that's the optimization that goes to it is exactly the same between the two approaches. The only difference is that the data, you don't have any neural network in the data-driven approach. The data is completely directly given to you. Whereas in the neural network-driven approach, the data, you probe it, you generate the data from a trained neural network. You're not given any training data. But you have a trained neural network. But that doesn't matter. You can probe the neural network. Now you get your data back, right?
Okay,
So
but just a quick question. I mean, since you said it's a trained neural network, that I agree.
Yes.
But when you said that we can use any neural network, whether it's a deep or shallow, for deep, definitely we cannot write down the analytical way expression for these.
Okay. So this is not okay. So this analytical equation is not exactly explaining how these things two are mapped. It's just fitting the probe data of the neural network. It's like a surrogate. So if you think about how people do post hoc XAI, the simplest approach is line. They take an input f of x, they perturb it, they fit a linear model to that. Now, is a neural network a linear model? Of course not, right? But the linear models like locally can provide a simple explanation. So that's kind of the same thing here, but in terms of integral equations.
Okay. Yeah.
It's not saying that the neural network is exactly working this way, right? It's just a surrogate for the neural network's prediction. Yeah.
And so second question was for the physics informed ADAM-SINDy, you're
Yes.
actually using the gradient of that gamma, right?
That's right.
So what's the reason of using?
Okay, not the grade. Let me see. We're using where is it? Okay, here. We are using the divergence of
Divergence. Sorry.
So that goes into the way. So this is now fixed. So in the previous case, this gamma was trainable, but now this gamma is like basically just a divergence. It's not trainable anymore.
Okay. So is there any reason to use this?
So you want this, when you're just doing this minimization, you want both of these to be zero, right? You want this to be as sparse as possible. You want it to fit data. And when you weight it, this is just what we tried, and it worked very well. The idea is that, okay, if we have the divergence, you just weight this multiply this by the divergence, then the algorithm optimization should kind of like make both of them close to zero, right? Both the sparsity and also the divergence. And that's exactly what we saw. And it was very interesting that it converges really fast in this case, so that I don't have a good explanation for that part. But again, this is the only example we've investigated with this physics-informed SINDy, because again, this is very limited cases, because you're talking about dynamical systems now, right? When you're talking about dynamical systems, physics-informed is a little bit like maybe Lagrangian Hamiltonian would be another example to investigate in the future. Yeah.
Okay. Yeah. Thank you.
Like Professor Arzani, like quick question on this slide that you're showing right now. So when you're saying that the divergence, when the divergence differential form as it is going to zero, like will it may or may not satisfy that the sparsity thing? So basically, you're trying to promote sparsity with that L1 regularization, but if you have the differential divergence differential form that is going to zero, do you think that might?
That's a good question. So that's a very good question. So the idea is that, so what we see is that we have to look into how fast each of them is going to zero. But my guess is that, so I haven't looked into that, but my guess is that, if you're converging to divergence-free velocity, there's a good chance that that's going to be basically the equation that you're looking for. Because now you're kind of like limiting the subset of these dense, complicated models that just fit the data, right? So that's kind of like how I see it. And again, in this specific ABC flow example, it works perfectly. But again, there's no rigorous proof or anything here. This is just empirical.
Right. I was just purely talking from that the optimization that standpoint from the way in which it is currently shown in the slide. So that's why I wanted because I assume the lambda that you're talking about in the slide is a fixed parameter and not a trainable parameter. The lambda would be
no, lambda is so gamma is fixed or calculated on the fly.
Yes. Okay.
But the trainable parameter is this lambda here. That's a nonlinear parameter.
And the smaller lambda, I was talking about the small lambda.
Oh, yeah, this one is, yes, this one is fixed. Or you
Fixed,
can, in this case, yes. In this case, it's fixed, or you can tune it. Yes.
Right. And also you showed in a couple of slides that when you do not have some understanding about the frequency of your underlying signal that you're trying to do with SINDy, for instance, the SINDy does not give you good approximation of the actual form of your equation.
Yes.
Is it also understandable? Is it right to say that if you do some trial and error or spend more time on tuning your lambda in SINDy, you might end up having the same form that you're expecting as a ground truth?
So you don't have, it's not about the lambda, it's about the frequencies, the nonlinear parameters you have to tune.
Okay.
And that's a very difficult business. So we've been struggling with this for the second part of the talk, which is the kernel approach, because in the integral equations, I didn't show you how the kernels look, but those kernels also have bandwidths, their exponential terms, which is you have to guess the range for them. And that's very sensitive to that guess. And that's what we spend a lot of time kind of there, tuning that. And of course, we're thinking about integrating ADAM-SINDy with the integral equation and operator learning approach in the future to overcome that issue. But that's the problem, is that these nonlinear parameters are not trivial to guess.
Right.
And yes, if you could guess them correctly in your library, of course, SINDy gives you this. So SINDy works perfectly fine. It's actually much faster than ADAM-SINDy. Now, you wouldn't even need ADAM-SINDy because this is slower than SINDy.
Yes.
Yeah.
Thank you. Yes. So I think if participants, if you don't have any further questions, then so I'd like to once again formally thank you for your time that you've spent in explaining your work with us, and also for this very informative session. Prof.
Amir,